Any questions? Remember that Wednesday next week we have a prelim in class. And I sent out an email the other day. I know that there's some people in the class who have direct class conflicts only on Wednesday. And if you have that, then please email me back as soon as possible, because I don't want to be making arrangements for people at the last minute. I want to try to synchronize everybody who's not going to be able to take it at that time. Okay. And the prelim from last year, the first prelim from last year, is available on Blackboard, and sometime this week I'll put up solutions for it. But I suggest you try to do it yourself before you see the solutions. And you'll notice that it covers only discrete time stuff, and that's going to be the case this year as well. The homework that's due this Thursday will be fair game for the prelim. So I want to have solutions out before the test, and therefore we're going to have a rigid deadline for that, perhaps Monday, if you don't get it done by Thursday. But you'll soon be getting emails pleading you to turn in homework 3, and then you'll get an email a day later pleading you to turn in homework 4, or else it won't count. So anyway, that's a scoop. Any questions about any of that stuff? All right. Okay, we're talking about these continuous time, linear time invariant systems, and today I want to finish that up and then move on to the next item. So where were we with this? We had definitions, we had examples, and the examples look just like the ones in discrete time, essentially. You know, the identity, pure T1 shift, averager, integrator. And then I defined this notion of a strictly convolutional system. And a strictly convolutional system is one whose system mapping is convolution with some decent signal h. And whose input function space, capital X, is d sub h, the set of all signals convolvable with h. And for a strictly convolutional system, we call h the system's impulse response. And much of the rest of the class last Thursday, we spent figuring out why we call it the impulse response, because we haven't even defined up to this point what an impulse is in continuous time. And in trying to explain why we call it the impulse response, we discovered it led us to this thing called the continuous time impulse. Also known as the Dirac delta function. And this is not really a signal at all. It's just a thing. It's an operator in a sense. But when we play with it as if it were a signal. So we sort of quote-unquote play with it as if it were. And one rigorous thing we can say about deltas is that this, any kind of an integral where you have a delta of tau followed by anything d tau, that means limit as a goes to 0, 1 over a integral p a of tau times the same anything d tau. And if you're ever in doubt about what's going on with the delta under an integral sign, you can always take something that looks like that and turn it into this and see what happens. And the very last thing we had in class last time was using this. We saw that delta convolved with x equals x for every decent signal x. if you plug in delta of tau, and then for the bracketed thing, you put x of t minus tau d tau, turn it into this rigorous interpretation, figure out what happens, you discover that. Modulo what happens at the jump points next. This actually converges to the mean value across the jump, but with decent signals, we never care what they're doing exactly at the jump times. And that's pretty much where we are. It's easy to take this last result and extend it a little bit. So it's easy. Got to learn how to spell. To show that if I take a shifted delta and I convolve that with any decent signal x, I get shift sub t1 of x for any decent x. And any t1. And I don't think we actually did that in class last time. You can look in the monograph and you'll see how that works. So delta is like an identity element for convolution, even though it's not really a signal. Moreover, the moral of these last two examples is that we can think of those, the identity system and the pure T1 shift system, which did not have this strictly convolutional property, we can think of them as being convolutional in some sense because you can implement them by convolving with either a delta or a shifted delta. So the upshot of this, even though the identity, and these are rather innocent systems, they never hurt anybody, but they aren't strictly convolutional. We can view them, we can, I don't know how you want to say this, you can quote unquote implement them by convolving with either a delta or a shifted delta. All right. So anyway, that's where we're at now. Now, what we had these example systems, and I told you what the impulse responses of the strictly convolutional ones we looked at, the averager and the integrator, were. I didn't derive that in any way. We'll talk a little bit more about that later today. And we have the shifts, and in particular the identity, which is really a special case of a shift. And those involve convolving with delta. So what we're going to do from now on, and this is an assumption, by the way, that most books kind of make without, even really talking about it. But it does restrict the class of systems we're looking at. So here's the standing assumption from now on. And really what this does is it says every system that we're ever going to want to think about is partly a strictly convolutional system and partly a pure shifty kind of system. How does this work? So every linear time invariant system has an S, system mapping S, that looks like this. S of x for any input x is going to be the convolution of some function h0, which is going to be decent. I'll tell you that in a second, with x, plus the sum from k equals 0 to, say, capital M of some numbers times shifts sub tk for some times tk. So, in other words, where h0 is a decent signal, and furthermore, it's going to have input function space d sub h0. And there's a few restrictions on the dk's and the tk's. So facts about the dk's and the tk's. T0, so as for the dk's and tk's, T0 is always going to be 1. Well, first of all, capital M is bigger than or equal to 0. And what does that mean? That means that it's possible that there's no term other than the D0 term. And T0 equals 0. D0 might be 0, but the dk's for k bigger than 0 are non-zero. So dk is not equal to 0 for k bigger than 1. And tk is also not equal to 0, k bigger than 1. And they're all distinct. Okay, now this is a big bunch of words, but it's a really simple idea. The simple idea is this. So simply stated, or stated simply, however you want to say it, all the systems we care about has a strictly convolutional part in quotes, and that's the first term in the I/O mapping S, and a quote-unquote pure shift part, and that's the rest of the terms. And either or both, or either one of those might be absent. If they're both absent, it's the zero system. But that's the simple idea. There's no more complicated I/O relationship in continuous time that we're going to want to consider. Okay? Terminology. The impulse response of this system or such a system, let me put it that way, is H equals, and I'm going to see if you can guess what the impulse response is defined to be, given that the I/O mapping of the system is that S over there. Now be daring, somebody. Zach.
H naught plus some over k and the dk times just delta. Okay, delta.
Yes, exactly. That's what it is. Okay, now, notice that if the system happens to be strictly convolutional, what does that mean? That means there's nothing, there's no sum term there. This reduces to the definition of impulse response we had before. And that's always a good thing. You know, if you're generalizing, you want to make sure that your definition, your new definition is back compatible, right? That's a good. No one in math books talks about back compatibility, but that's what's really going on. See, nowadays teenagers know what back compatible means, right? And they also know that companies that produce new software that violates back compatibility are anathema to smooth existence or whatever. So note, if the system is strictly convolutional, h equals h0 as before. Okay? But in any event, we can, again, interpret this impulse response in at least two ways. First one is, it's the response to an impulse, h equals s of delta. Even though the impulse is not a signal, we play around with it as if it were. What happens when we play around with it as if it were a signal and we plug it in to the definition for s? It's h0 convolved with delta plus the sum from k equals 0 to m of dk shift sub tk of delta. And why is h0 convolved with delta equal to h0? Because delta is an identity element for convolution. The other interpretation, h is what you convolve with input signals to give you output signals. That is to say, s of x for any input x is equal to h convolved with x for all x in the input function space capital X, which by restriction, by standing assumption, is d sub h0. So impulse response has the same two interpretations in continuous time as it did in discrete time. Great thing. And you may say, well, hey, yeah, this restricts the class of systems we're allowed to look at. How restrictive is that? It's really not very restrictive at all. You can model pretty much anything, any continuous time thing you would encounter, a linear continuous time thing that's time invariant, using something like this. Like the shift terms, they help model things like long transmission lines and stuff like that, where you have a delay from point A to point B. The convolutional part, well, we've seen that a lot. So, it's a good class of systems, and it's not. And the reason we make the standing assumption part of it is because we want, once again, we want to have a kind of compact characterization of the system. We want to be able to talk about properties of the system in terms of properties of something else, and it's simpler. And in this case, the impulse response tells you the whole story about the system. I just noticed this thing is up, which blocks some people's view. Yes? Because it's wrong. K equals 0. Yeah, thank you. And what's your name? Judy? Okay. I didn't know that before, did I? Okay. All right. So anyway, that's the standing assumption. Now we're through with all the kind of, unpleasant contortions you run into in continuous time, having to do with deltas, having to do with things that aren't really signals, but we pretend they are, blah, blah, blah. Now we can move on to, looking at our example systems, first of all, again, and see what their impulse responses are using this new h equals s of delta thing, and then talking about system properties and how they get embodied in the impulse response. So let's find impulse responses of the example systems. Now, you might remember that last time, when I told you that, I just kind of told you that the averager system and the integrator system were strictly convolutional, and here are their impulse responses. Now we're going to derive that using h equals s of delta. But first, let's look at the identity and pure T1 shift. So the identity, the zero system, H is equal to 0. The identity system, what is H equal to? What's the impulse response to the identity system? Nathan. What's that?
0. Oh, no, sorry.
Delta, right. Okay. You can think of this in either of those two ways. If I put a delta into the identity system just passes the input right through, so I get a delta out. Or, delta is the thing you convolve with any decent x to get x back, because it's an identity element for convolution. Pure T1 shift, what's that going to have as its impulse response? H equals anybody? Yeah.
Shift T1 delta.
Shift T1 of delta. Okay, now what's your name? I still haven't learned it yet.
James.
James, okay. Okay. Now, what about the averager? What about the averager? I told you earlier what the averager's impulse response was. And I didn't prove it. I just said it's easy to check that this is the case. But let's do H equals S of delta and see what happens. Just to see what happens. So the averager, I told you before, so stated without proof, that H had specification H of t is equal to 1 over t when t is between 0 and cap t and 0 otherwise. Now, what I want to do is I want to derive this using H equals S of delta, and what we're going to find is a tiny discrepancy. And the reason I'm going through this derivation, at least in part, is to point out that we don't care about that tiny discrepancy. Okay, so let's prove this, quote unquote, prove this using H equals S of delta. Fair enough? Okay, so what's the description of how the averager system works? If I take S of delta, so by definition of the system, by definition of the averager system, S of delta has specification S of delta of t equals 1 over cap t integral from little t minus cap t to little t of delta of tau d tau for all t. How do we deal with an expression that has a delta under an integral sign? Until we're really good at it. What we do is we go back to interpreting deltas under integral signs in a rigorous way. So this is the same as 1 over cap t times the limit as a goes to 0 of 1 over a integral from t minus cap t to t of pa of tau d tau. Okay, now let's draw a little picture over here. First, get rid of this computer science-like thing. Although I don't really know what it. Does anyone know what that is? What's that? Networks. You mean networks as in Kleinberg and Tardish and company?
No, it's a post-class.
Oh, okay. Okay. It's ethics, isn't it?
Yeah.
Like that guy who was here the first couple days, but anyway. T minus cap t up to t. Can everyone see that? Or is it buried below this for some people? Anyway. We're integrating a PA of tau over that tau interval. And we're taking the limit as a goes to 0 of 1 over a times that. So what if there's three cases. One case is when the pulse is over here. One case is when the pulse is over here. Well, there's actually more. One case is in here, and one case is where it's right on top of that. Okay? See that? And what happens when it's in here? In other words, when 0, this is 0, the middle of the pulse, is between t minus cap t and little t. Let's open up another board. Actually, it would probably be better if I did it this way. If I put the tau number line up here, and I mark down 0, and I put the PA here, so this is 1 over a PA, say, and then consider the following cases. If little t is there, or if it's in between, or if it's over here, or if it's right on 0 on either side. So let's consider first the non-borderline cases and see what this comes out to be. What happens when little t is less than 0? When little t is less than 0, and that's the first one I drew, the PA, the 1 over a PA, isn't in the interval of integration t minus cap t to little t, right? Therefore, it comes out to be 0. What if t is in the interior, or if 0 is in the interior between little t minus cap t and little t? That's the second one I drew, the one directly under. Then the whole pulse is in there. When I integrate 1 over a times it, I get 1. And I have a 1 over t leading off. So I get 1 over t when 0 is less than t is less than cap t. And when t minus cap t is bigger than 0, I get 0 again. And t minus cap t bigger than 0 is the same as saying t bigger than cap t. But what happens when little t is exactly equal to 0? Or when little t is exactly equal to cap t? Let's consider those cases. I'll just look at the 0, 1. The same thing happens for the one on the other side. If little t is here, equals 0, and t minus cap t, which is minus t, is over here, then for every a, the pulse is always going to be centered on little t. And when I integrate 1 over a PA over that interval, t minus cap t to t, I'm going to be capturing half of that pulse and not capturing the other half. So what I get instead of 1 is 1/2. I get that for every a. So I let a go to 0, it stays 1/2. The same thing happens when t equals cap t. So this is equal to 1/2 when t is equal to 0 or t equals cap t, the mean across the jump. Compare that to what's directly above it. It's the same except at the jumps. So when we do h equals s of delta, we get the same as h before, except at the jumps. But we don't care about that. Those exact values don't matter. And that's a point I tried to emphasize when we first talked about decent signals. So if you do this, if you ever do this kind of a manipulation and you come up with something that disagrees with the previous answer you got only at jump points, that's nothing to worry about. And that's what we've got here. All right? And you can do the same kind of thing for the integrator. I won't go through that because it's really just the same kind of thing. You could try it for yourself. So for the integrator, we stated before, without any kind of a proof, that h equals a unit step. What you find when you do h equals s of delta is h of t equals 0 when t is less than 0, 1 when t is bigger than 0, and 1/2 when t equals 0, which is essentially the same. It's the same as a unit step except at its jump point. Okay? So this is same as before for all we care, or whatever. Yeah, Balash.
Why is it not 1 over 2 big T? Like, just 4.
Oh yeah, 1 over 2t. I'm sorry. Yeah, it's 1/2 for the unit step, and because there's a 1 over t leading off all these guys. So I got it right up here, but I didn't get it right down there. Thank you. Everybody catch that? This is what it looks like. If you want to be really specific about it. Okay, so those are the impulse responses of our samples, our example systems. Good. So impulse response, it's a response to an impulse. It's what you convolve with inputs to give you outputs. All that good stuff. Any questions about this? And again, all this stuff in one form or another you can find in the monograph. And I don't know if you've been reading your email or anything, but I revised the continuous time systems chapter over the weekend so that it matches up better with our discrete time systems chapter. And I'm almost done revising the periodic chapter, which is what we're getting to next. Okay. I'm wondering whether I should start calling out people in the class who aren't here so that they can see on the video note. I'll just do it for one of my favorite people. Okay. Hi, Ricardo. No, actually, I'm saying hi to Ricardo because just now I was upstairs delivering something to Charlene, and she said, "Does Ricardo owe you something?" And I said, "What? What?" You know, and then I walked out of her office, and there he is slinking by with his hood down, you know, as if he's trying to avoid me. And I said, "What's up? Why did Charlene just say, 'Do you owe me something?'" And he said, "I'm not going to be in class today." And I said, "Well, you weren't there last time either." He said, "I wasn't?" So he didn't even remember whether he was here last time. So anyway, I hope you're having a good... he wouldn't tell me why he wasn't coming, so I said, "Why?" He just kind of, you know. So, does anyone know why Ricardo's not here?
I think he's doing
Comp arc?
He was asking me to read like a sample code earlier.
He's a sophomore. He's not taking comp arc.
He is.
Oh, he's a second year junior. Yes, yes. Fair enough. Okay, I don't want to share all of his details with everybody. So anyway. Okay, so that's our call out for today. Will you be next? Okay. So, as in discrete time, we have some important system properties. And we have corresponding embodiments. In terms of the impulse response. Okay. And the definitions of the two properties we want to consider, causality and BIBO stability, look almost exactly the way they did in discrete time. So a system is causal when what? When the colloquial definition is, for any time t, the current value of the output depends only on the current and past values of the input and not on the future values of the input. So for every t in the reals, S of x of t depends only on x of tau for tau less than or equal to t, and not on x of tau for tau bigger than t. And that's good enough. I'm not going to write, you know, if the official definition is if you have two inputs, x1 and x2, that agree up to and including time t, then the corresponding outputs have to agree up to and including time t. But that's the same idea as this. What about the impulse response is equivalent to causality? And so here's the fact. A system with impulse response H equals H0, the decent part of it, the strictly convolutional implementer, plus the sum from k equals 1 to m of dk, shift sub tk of x is going to be causal if and only if the following conditions hold on H. So what are those going to be? What do you think? Remember in discrete time, it was h of n is 0 when n is less than 0. H impulse response doesn't turn on until time 0. Right? So what do you guess is going to be true? What has to be true about the H for the system to be causal? Yes, it's k equals 0 again. Thank you. If you think of H as the response to an impulse, even though the impulse isn't even a signal, or shift T1 of delta, that should be a delta, not an X. If you think of H as the response to an impulse, and the system is causal, the same thing is true again. Yeah, Ian.
If H is 0 for t less than 0.
Yeah, that's what, but okay. So I'll put that in quotes because that's approximately true, okay? Quote unquote, h of t equals 0 for t less than 0, unquote. Meaning what? Well, what it means to me, because the reason I'm being picky here is because these deltas, these shifted deltas, they're not even signals. I don't even want to talk about them being equal to something, whether it be 0 or something, 10 to the 59th, whatever. What this means is that h0 of t is 0 for t less than 0, and all the tks for k bigger than or equal to 1 are positive. And we don't have to consider t0 because by definition t0 is 0. That's the quote-unquote pure identity part of the system. And that does not say anything about deltas equaling anything. So that's why I'm ditching that difficulty by saying it that way. That's what it means for, in terms of the impulse response for a system, be causal. Does everyone get what the dead horse I'm beating here about not having deltas be equal to 0 or anything? I feel like, it's one of those guilt trip things where, sometimes when you're a teacher, like you lie awake at night and you worry about, saying something that's not quite right and pretending it's right, pretending it's true, And so, I don't know, like, basically, here's the deal. I will never lie to you, okay? But sometimes the whole truth is too hard. So I won't tell you the whole truth. But I will always try to remember to tell you when I'm not telling you the whole truth. Is that, so the Dark Knight said that, or? Anyway, okay, well, now that's a good time for the 3-minute break. We'll do BIBO stability after.
I don't remember Batman saying.
And what about BIBO stability in terms of the impulse response? The system is BIBO stable when its input function space, input signal space, contains all the bounded descent signals that is to say, capital L infinity decent signals. So not only are the bounded signals in there, but if you use one such signal as an input to the system, so for any such signal, the output, S of x, is also bounded. It's also a bounded signal. I got it. Oh, thank you. Okay, so essentially the same definition as in discrete time, except for the D word. Okay? And what about BIBO stability in terms of the impulse response? System with impulse response H equals H0 plus the sum from K equals 0 to capital M decay shift sub Tk of delta is BIBO stable if and only if H0 is an L1 signal. That is to say, H0 is absolutely summable. Integrable. Now, why doesn't this impulse response-based criterion for BIBO stability allude to the decays and the TKs? Why don't they have anything to do with determining whether the system is BIBO stable? Any suggestions? Yeah, it's a finite. Who said that? Yeah, Nathan. It's a finite sum. And if you shift a bounded thing, you get a bounded thing. And if you multiply it by a finite number, you get a finite bounded thing. And if you sum up finitely many of those, you get a bounded thing. So that's never going to give you a problem for BIBO stability. The only thing that could conceivably give you a problem is this part, the strictly convolutional part. And I might add that some people, when they define these systems, they allow infinite number of terms in the shift part. And if you do that, you're going to have to assume that for BIBO stability, that the sequence of decays is a little L1 sequence. It's absolutely summable. And there is a practical application, see if anybody can guess, where it makes sense to model a phenomenon as having an infinite number of shift terms. What would that be? What might that be? Can you think of an example? Something that actually happens in real life. Okay, let's see if I can give you a hint. I'll just tell you. It's the idea of an echo sort of thing, right? You send a signal, it bounces off of something, comes back and bounces off of where you sent it, bounces back to the thing, bounces back, and so on, right? That comes up a lot in real life. Alex, it doesn't? No, it's something else you're talking about. Okay. All right. Now, if you think of every time it makes one of these echo passes, it loses a little bit in amplitude, like let's downgraded by like alpha, where alpha is less than 1. Then the decays are going to be like alpha to the k, where alpha is a positive number that's less than 1. So the decay sequence in that case is going to be a little L1 sequence because of the geometric series. And you will actually see kind of a related example to that on the homework coming up after fall break. Actually, 2 versions of the same problem where it talks about multipath kind of phenomena. All right, so before we move on, let's consider our example systems, just without even writing anything down. Decide whether they're causal, whether they're BIBO stable. So by acclamation, is the zero system causal? Is it BIBO stable? Speak.
Yeah.
Yes, okay. How about the identity system? Causal? I'm not looking. You can say no and I won't see you. Okay, causal? BIBO stable? Okay, pure T1 shift causal? Sometimes. When T1 is bigger than or equal to 0, yes. And when T1 is less than 0, no. BIBO stable? Yes. Causal sliding window averager? Causal? No. Yes. And BIBO stable? How are you deciding? Okay, there's some disagreement here. Okay. Some people think the causal sliding window averager is BIBO stable. Some people think it's not. Okay. For the moment, forget about BIBO stability in terms of H0 and L1. Just think of the definition of BIBO stability. BIBO stability says that every bounded decent signal is admissible and gives rise to a bounded output. Okay? What does the averager do? What does the averager do to a system? It takes the input signal and it puts out a sort of a smoothed out version of the input. It takes that input signal and at time t, it averages the values of that input over the previous cap t. Now, if the input comes in and it's always under some ceiling and above some floor, its average value over any length of time is always going to be under that ceiling and above that floor, right? Ergo, bounded in, bounded out. All right, so that's the answer for the averager. And if you do think of this theorem here about L1 impulse response, the impulse response of the averager is just that finite width pulse, and clearly that's absolutely integrable. So if you want to do it that way, you can do it that way. But I think it's better to go back and think about the definition, think about what the system does. All right, finally, the integrator. Is that causal? Yes, it is, because quite explicitly, the output at time t depends on the past of the input and not on the future. Is it BIBO stable? No. No, you can't even put a constant into the integrator. You can't, and you know, it turns out you can put a unit step in. That's a perfectly allowable input, but it leads, and it's bounded, but it leads to an unbounded output because it grows, it ramps up like t. All right, so that's what the example systems are in terms of BIBO stability and causality. And as in discrete time, you can prove a stronger result on BIBO stability. It turns out that a system is BIBO stable if and only if for every bounded right-sided signal, you get a bounded output signal. So you only need to check right-sided inputs. But that's too advanced. It's in the monograph. You can read about it if you want. And I'll leave the system stuff at that. So any questions about this material? It's all pretty parallel to discrete time. Just to highlight the issues that make it different. Number one, the whole decent signal bit. Okay, we want to restrict our attention to signals that aren't horrible. Number two, the impulse in continuous time, unlike in discrete time, isn't a real signal. Isn't a true, I shouldn't say real, because that has a technical meaning in this class. Isn't a true signal. But we play like it as if it were. And so we can't sort of right away, as in discrete time, say, put an impulse in the system, this is what comes out. We have to be more careful, more circumspect. Strictly convolutional systems, those are essentially universal in discrete time. But in continuous time, no. Some innocent systems like the shift, the evaluator, the whatever, the identity are not. So if we want to allow for those systems, we have to bite the bullet and have impulse responses that look like that actually have deltas in them. So those are the main points of difference. And everything else is pretty parallel. And as far as the signal theory goes, the convolutions, the convolution criteria all look exactly the same, except the decent word comes in. And, you know, so I'm hoping that having seen it in the cleaner sort of, I don't know, more discrete context of discrete time, it makes sense in continuous time, and it's not too, you know, too much of an analytical hassle. All right, so moving right along, the next big topic, and here, by the way, I'm going to try to take advantage of your awesome training from ECE 2200 that you got from Professor Tong and Professor Dorshuk, those of you who took it from them, and your rookie training in ECE 2200 that you got from me last spring, because that was the first time I ever taught the class. And I'm not going to go into as much detail as I usually go to on some of the points here, because I want to get to the mathematical heart of the matter, the new stuff. So as we go along, I'm probably going to give you some bullet point, highlight reel kind of things. And if you want, you can read about them in the monograph, but you can also look at the video notes from fall 2011 if you want to see me talking about it and talking to folks in class about it. So anyway, the topic we're going to be talking about now is basically, it's sort of like, you know, when you were a kid and they wanted to give you an aspirin or something, they would crush it up and put it in applesauce or whatever. I don't know if they still do that. What did your... Sounds so sketchy? Yeah, it sounds like, you know, you're slipping your kids drugs or something. Okay, so what I like to think of in that case is that the applesauce is a vehicle for aspirin. Okay, and a friend of mine used to say to him, French fries were a vehicle for ketchup. You know, he liked ketchup and he didn't like French fries, and so he put up with the French fries just to eat the ketchup. I'm sort of I don't like ketchup on French fries. But here, what we're going to be doing is what I call periodic signals and Fourier series. But only as a vehicle for discussing orthogonal expansions in inner product spaces. Okay, so that's the topic I really want to get across, this idea of orthogonal expansions in inner product spaces. Now, why? Well, it's getting more and more sort of in the foreground of what you have to know to understand signals. And wavelets, which we're going to try to talk about for at least 1 or 2 lectures, that's a classic example of another kind of orthogonal expansion in an inner product space other than Fourier series. And since you've all seen Fourier series before in several different forms, I think, I'm hoping that that will be a sort of comfort zone in which to process this new info about orthogonal expansions in inner product spaces. Okay, so Fourier series. Now, you saw those, did you see those in, I already asked the class last spring, you saw them in 1920 or 2930? That is to say, multivariable or, okay. So diffie-q is where you saw them the first time, right? Then you saw them in 2200, if you took 2200. Right? No matter who taught it, you saw them. And you saw them in both complex exponential form and sine-cosine form, right? Yeah, okay. So what I'm going to do is I'm just going to rattle off some highlight reel kind of stuff. Okay, so some sort of highlights without much elaboration. And like I said, if you want to see more about this, look at the old video note and or read the monograph. And this is going to be about periodic signals and Fourier series in general. Okay, so most important thing, what was Fourier's first name, or first 2 names? Anybody know? Hurry up, quick. Ah, okay. Jean-Baptiste Joseph Fourier. Yeah. Okay, and what did he do? What was he? He was a mathematician. He was a French dude, interested in heat flows and all that kind of stuff and whatever. So he was a really smart guy. But anyway, okay, so what does it mean for, and we're going to assume all the signals now are complex valued. So assume, and this is going to be true for most of the rest of the class when we talk about like DTFTs and all that stuff. So assume, without loss of generality, that signals are all complex valued. And so we're going to be dealing with R, or C to the R, the set of all complex valued signals in continuous time. So I won't be writing F to the R as much as C to the R. Okay. X in C to the R is periodic. What does that mean? It means that shift sub cap t of x equals x for some cap t. That's what periodic means. You can shift a signal by some positive amount and get the same signal back. And our notation with a shift thing makes it easy to write that down. And such a t is called a period of x. All right. A decent periodic signal x has a smallest period. We call that the fundamental period. Okay, now, decent. Why do we need decent here? Think about the most indecent of all of our indecent signals. The one that's equal to 1 when t is irrational and 0 when t is rational. Every rational number happens to be a period of that signal. Therefore, that signal has no smallest period. If, however, x is decent and periodic, it has a smallest period, and we call that the fundamental period of the signal. And all this stuff, by the way, you can prove it mathematically. It's in the monograph. You can read about it. Now we're going to use some standard notation. If I'm given some cap t0, it's positive, I'm going to use the notation capital X sub t0 to be the set of all decent signals x, complex valued signals x, that have t0 as a period. Not necessarily as their fundamental period. Okay? Fact, xt0 is a subspace of c to the r. In other words, it's closed under taking linear combinations. If you have two signals that have t0 as a period and you take a linear combo of them, then the corresponding linear combo will have t0 as a period. And it's closed under shifting. So it's got that good property that we like of being a subspace that's closed under shifting. And there's a lot more in the monograph about this. Like, I used to, in the 2011 class, you can look on the video note, we do this vote. Say, how many, and we did this in 2200 last spring. How many people think if I take a linear combination of periodic signals, I get a periodic signal? Yes, no. Well, it turns out that it's not always the case. The periods have to be related, rationally related. The ratio of the two periods has, or they have to catch up with each other. Remember that from last spring? Yeah. And you can actually prove that. And so there's more to this. But the set of all signals that have t0 as a period, that is a subspace. It turns out that the set of all signals that have t0 as the fundamental period is not a subspace. Okay? And you'll have homework about that, and it's also in the monograph. Okay, so given this setup, here's the big theorem. due to Fourier and others who followed him. If x is in capital X T0, in other words, if x is a decent signal that has T0 as a period, and x satisfies certain conditions, namely I'm just going to say certain conditions today, and next time I'll tell you what they are real quick. Then you can expand x in a series like this. X of t is equal to the sum from k equals minus infinity to infinity of ck e to the jk, what I'm going to call capital omega 0 t. In this course, we're going to use capital omega for a frequency in continuous time and little omega for discrete time for reasons that I won't go into now. And here, omega 0 is 2 pi over T0. And the CKs are given by the following formulas. The formulas are C0 is 1 over T0 integral sub T0 x of t dt. And what does this notation mean? It means integral over any interval of length T0. I'll write that down in a second. And ck is 1 over T0 integral sub T0 x of t e to the minus jk omega 0 t dt. When k is not equal to 0. The only reason I separate these two is that I want to exhibit C0 for what it is, namely the average value of x. So that integral sub T0 notation means quote unquote integral over any interval of length T0. Okay. And what do we mean by expanding x in that series? The certain conditions and I'll just tell you what they are, basically. X is decent, and in the intervals between jumps, it's what's called piecewise differentiable. You can have corners, you can't have cusps. The certain conditions guarantee that the series above converges for all t and if t is a continuity point, a non-jump for x, it converges to x of t. It converges to x of t when t is a continuity point and to the average value across the jump when t is a jump point. Okay, so that's the big theorem. Now, there's no way we can prove that in this class. This is lots and lots of work, and the certain conditions, come in a really complicated way. But this is the big theorem at the core of Fourier analysis, and this is what I mean by I'm just going to give you these highlights to start with, because you've seen this all before in one context or another. Because what I really want to do is get to a recasting of this whole thing in terms of orthogonal expansions and inner products. So let's leave it at that for now, and we'll pick it up tomorrow.